Hi, welcome back to another video about Python, and this is the part 2 of ordinary differential equation with boundary condition. If you haven't watched the part 1, please watch it because this one is only another example, and there are many concepts that I will reuse from the part 1 in order to demonstrate this example, another example of solving ordinary differential equation with boundary conditions. And this is our problem. So if you haven't watched the part 1, please watch the part 1 because this is all the concepts that I reused from the part 1 of watching ordinary differential equation with boundary conditions. And now goes to this example. We can see this is the example. We need to find a solution function y of x, where we have the second derivative of y with respect to x equal to 2 plus x times y in the range of x from 0 to 1. So the boundary values of x is 0 and 1. Now the input information given to us is that for the function of y at the value of x equal to 0 is equal to 0. So this one is one boundary condition, and the other one is the first derivative of y with respect to x at x equal to 1. It looks somehow similar to the initial condition in the previous video. If you watch the videos, the part 1 of this boundary condition, ODE, you will notice that in that video we also have the first derivative of the function. However, the value of the first derivative is evaluated on the same boundary with the zero derivative. That was in the previous video, where the first derivative is evaluated at the same value of x or the same value of the variable with the zero derivative. However, when you look at the zero derivative here, the zero derivative is the function itself, is evaluated at the boundary at x equal to 0. However, the first derivative, y, is evaluated at the other boundary at x equal to 1. The value of the first derivative at the other boundary where x equal to 1 is 5. So there's a slight difference from this input information compared to the input information of the initial conditions in the previous video of ODE with boundary condition part 1. With this slight difference, it makes the whole problem change to the boundary condition instead of initial conditions. The method that we used in the part 1 to solve the boundary condition is to use the shooting method, where we perform two steps. The first step is to transform our boundary conditions to the initial conditions, the equivalent initial conditions, and after we got the equivalent initial conditions for our function, we move to the step 2, where we already got the equivalent initial condition. So now, based on that initial condition, we can find our solution y function of x as if we are solving the initial condition ODE. Okay, now for the step 1, this is also a concept I already introduced in the part 1, so please watch it. But this one I just slightly saying that we need to define a function or a system where we gonna use an input to the scipy.optimize.newton, and the input also the root of the system, and the root of the system here is the first derivative, evaluated on the left boundary of x, which is x equal to 0. You must notice that this is the first derivative on the left battery where x equal to 0. However, on the output, we want to have the output is the first derivative on the right battery where x equal to 1. So that's the difference. And one more time, because we're gonna use this function as an input to optimize Newton in order to take advantage of the optimized Newton iterate to find our appropriate initial condition, equivalent initial condition to our battery condition. That's why we need to conform to the requirement of the function that we input to the optimized Newton. And the conformant is that our system must give an output equal to 0. However, the one that we want to find is equal to 5. The one that we want to define as an output of our system is equal to 5. So how can we transform equal to 5 to 0? Of course, we just need to take the left side and subtract the right side and equal. Then that one will be 0. And this one and this condition, they are the same. And after we define the function input to the optimized Newton, we can easily find the corresponding initial condition. And after that, we can solve our problem. However, we have a system here, and this system is a complex system. So how can we define that system? Of course, that system have to, if we pay attention to the pattern of the input and the output, and also the system need to reflect the problem, which is the second derivative or the second order ordinary differential equation with a range of independent value of x from 0 to 1. That pattern reflects the pattern of a function input to the scipy.integrate solve IVP. Scipy.integrate solve IVP will, as a general, represents our complex system, and that complex system will be wrapped up as a function input to the optimized Newton in order to find the corresponding initial condition to our battery condition. So that's the very complicated step 1 of the shooting method. But however, after we finish the step 1, the step 2 is very straightforward. When we already have the equivalent initial condition of our function, we just need to use it with the normal solve IVP and find our solution. And we can check our solution to see whether it conforms to the requirement of the problem. And that's the end of the concept introduction. Now let's move on to the code. Okay, you can find the link to this code in the description of the video, so please just be fine. And here is the example number 1. The example number 1 has been demonstrated in the part 1 of the ODE with battery conditions. Please watch it if you haven't watched it. So now this is the example of part 2. First, we need to go, even though when we do the concept or when we derive some ideas to solve a problem, we go from outside to inside. We go from top to bottom. However, when we solve the problem, when we already got the idea how to go from top to the bottom, and when we start to really implement that idea, we will go from inside to outside, or we will go from bottom to top. That's why we first need to define our function. And our function, we need to define our system, and this is our system. And our system will be represented by the solve IVP, so we need to input a function to the solve IVP, and that function reflects the ODE that we need to solve. And this is the function reflects the ODE that we need to solve. If you don't understand why I can define this function input to the solve IVP, please watch my video about the ODE with initial conditions. I put also the link in the description. You can watch it in order to understand what is the format of the function input to the solve IVP. But now, here is our system. And this is the function input to our system reflects. This one reflects our ODE need to solve. And here's the range of our variable this is the battery where x equal to 0, and this is the right battery, another battery where x equal to 1, and the initial condition will contain first the gas, or this is not the gas, actually this one is the value of the function at x equal to 0, and this is our gas. This is where the optimize Newtons will start to iterate and find the appropriate or the corresponding initial condition to our boundary condition. Okay, so this is our system, and this will be the function that we input for our optimized Newton. This is the function that we input to our optimized Newton, and the output need to be modified a little bit in order to reflect the boundary condition and conform to the requirement of the function input to the optimized Newton. And as I have a small notice here, if you're gonna use the solve IVP to solve a second order differential equation, then in the solves it will contain, the solve y will contain two functions solution. The first function solution is our function itself, but the second function solution returned by the solve IVP is the derivative of our function. Okay, and because the battery in our case is in the first derivative, that's why we need to extract the first derivative and the last value of the first derivative function. Subtract to 5. Now let's run and check. Okay, now I define the system, and now I will define the function for input to the optimized Newton, and then I run the optimized Newton to find the solution. So this is the corresponding initial condition to our boundary condition, and we already started in here, so we just need to input this one into solve IVP with the same system that we need to find our function, and then we solve it. And here we will check our first derivative function to see whether at the value of x equal to 1 at the right battery, whether the first derivative has the value of 5 as we required. And now look at here. So this is the battery x equal to 1, and if we look on the y-axis, it reflects the first derivative of the y, and it is 5. It's 5. And if we're gonna plot, let's say I will plot another figure of our function, not the first derivative function, but our function, to check the other battery. So the other battery is, sorry, this one should be y. So this is our first derivative. We check the right battery where the first derivative must be equal to 5 and is correct. And then we check our function where x equal to 0 reflects the left battery. The value of the function should be 0 and is 0. So everything conforms to the requirement of the problem. And that's the end of solving another example of ODE with boundary condition. And thank you so much for watching. See you in another video. Goodbye.